Okay. So last week you learned about sets, about probability, definition of probabilities, and you learned about conditional probability. So today we have an example. So this is an example. Assume that we have outcomes equally likely. So this is the omega is the big one, the big rectangular A. You have the set. The outcome A is here, and you have the outcome B. So I already compute what is the number of element in omega, number of element in A, B, and the intersection of A and B. So I have a first question for you to. Where is this? Okay. We have three. First question. Can you scan the barcode here, and then you can answer the question. Question one is compute the probability of A given B. And question two is probability of B given A, and then the last one is the probability of complement of A given B. Okay, so we have a look at response 2/5, 0.4. Yeah, it's 2/5, right? Because we have assumption that the outcomes are equally likely, which means that the probability of A intersect with B equals to the number of the elements in the intersection of A and B and divided by the number of elements of omega. And the probability of B equals to the element of B divided by the number of elements of omega here. So which is the fraction of the number of elements of the intersection here is 2 and divided by the elements in set B. It is 2/5. And the probability of B given A, so similarly you will have is the equals to the number of elements of A intersect B divided by the number of elements in A, which is 2/9. And the complement of A given B, so it's 11/5.
It can't be, because given B means that there's only 5 objects to choose from, and there's only 3 models that are in the complement of A.
Yes. 1, 2, 3. Yeah. Okay. I guess you have no question for this example. So, do you have any notice about the conditional probability? What? So about the conditional probability, if I fix a set B, so if I have a probability of a set B positive, different from 0, which means positive, right? Because probability is a positive measure. So if I have a set B, outcome B, event B have a probability greater than 0, different from 0, then you have, if you have a look at the probability as a function given B, fixed B, and this one you can put like any subset of omega. So this one is a function. This function mapping from sigma omega into R. What is sigma omega in algebra? Sigma algebra of a set omega. Sigma algebra of a set omega is a set of subset of omega satisfy the condition that it is closed for countable union and countable intersection. So we call sigma algebra of a set of omega. So which means that if I take any A is a subset of omega, then I have a mapping. Probability of A given B. So this is a mapping, right? So now you can see that this mapping is a measure function positive, because from the definition of the conditional probability, you see that probability of A given B positive, right? Which for any A is a subset of omega. Because this one, from the definition, is probability of A intersect with B divided by probability of B. Probability of B different from 0, positive. Probability of this set greater or equal 0, which means, yes.
Sorry, so what is the sigma of omega?
Sigma of omega is a sigma algebra of a set omega. It's not included in this course, but if you learn about algebra, you will see that actually probability is a measure function. And a measure function in a general setting is defined on any sigma algebra of omega. Okay, sigma algebra of omega is defined by, this is a collection of subset of omega and satisfy that union, countable union belong to this collection. Intersection, countable intersection also belong to this collection. If you have a collection of subset of omega satisfy these two properties, then they call this is a sigma algebra of omega, or sigma algebra of omega. For example, if you have sigma algebra, you have omega, and you can construct a very simple sigma algebra, just include the empty set and omega, and also add the complements. For any A in sigma algebra, then the complement also belongs to the sigma algebra. So this one is a simplest example of a sigma algebra, just including the empty set and the set itself. Okay, simply speaking, it's just a collection of the subset of omega. Okay. So, but the important thing is that I want to show that probability, conditional probability given set B is a measure, is a probability, is another probability. Okay, so this mapping positive. For any set A is a subset of omega, I have this property positive, right? And I have also another property that you have one probability of rather than A, I choose omega. Then I have this one is 1. Just from the definition, so it's equal to probability of omega intersect with B divided by probability of B, and this one is probability of B over probability of B, right? And this is 1. So you have this function, positive, and probability at omega is 1. And you have another property for the measure property function, which is that the probability of the union destroy event equals to the sum of probability, which means that you have the last equality. Probability of, rather than the green one here, I have the union of AI, where AI is destroyed countable. Given B equal to the sum of all probability of AI given B. So how can we prove the last inequality? If AI destroyed. So I want to prove the last inequality. To make sure that the probability, conditional probability given B is also another probability. So to just use the definition of conditional probability. So just imagine I write in here, the whole union is a set. The whole union is a set, one set. And then you have probability of a blue set, condition B, equals to, from a definition, equal to the probability of the blue set intersect with B divided by probability of B, right? So this step is just from the definition of conditional probability. And then what is the union, what is the set B in the set blue set intersect with B? Union of AI, I from 1 to infinity, intersect with B. So this one equals to union of AI intersect B from 1 to infinity, right? Do we need to prove it, or we have it? We have it? We already proved it, right? Okay, so fine, just use it. Then
isn't that distributed
prove that the left-hand side is a subset of the right-hand side, and then the second step proving that the right-hand side is a subset of the left-hand side. Then you have the equals. Okay, so then use that equality. You have the top here is the probability of union of AN intersect with B. So I write in green color. So now imagine that the green color is just one set. And then you see that all of green color are destroyed. Because you have AN destroyed. What does destroy mean? What is the meaning of destroy? What is the meaning of destroy? What is the definition of destroy? Empty intersection. For any, from definition, AI intersect with AJ equal to the empty set for any I different from J. So this is disjoint, right? So now if we have AI, a sequence of set AI destroy, can we deduce that the intersection of AI and B for any I also destroys? Can we prove it? It's quite easy to see, right? Because AI intersect with B is a subset of AI, and AJ intersect with B is a subset of AJ, and because AI intersect AJ is empty set for I different from J, so which means that this is the subset of AI, which means that this set also destroy. So here, this is AI and AJ destroy. So you have the intersection is empty, and then you have B. For example, B is here. Then the B intersect with AI is this one, and B intersect with AJ is this one. So it's also destroyed. Right? And because they destroy, so you can using the property, destroy event property of the property P here, this one, this P. Then you have the probability of union of destroy family set equals to the sum of probability, right? Sum of probability of the green set. Then now plot everything together, glue everything together, you see that the left hand side here will equals to replace this one by the sum of probability of A and intersect with B. So you have this. And just take the sum outside because B is positive and finite, so you can put this one inside of the infinite sum. And then this one, we write in terms of the conditional probability. It is the probability of A n given B. This one. Then you finish your proof. Just using the definition of conditional probability and using the third property axiom of probability P. Do you have any questions? Okay. So we prove that probability, conditional probability is also another probability. Okay. So now we go to the property of conditional probability, which is they call multiplication rule. Multiplication rules was that we can see that from the definition of conditional probability, then we can use it to compute the probability of intersection of two events, right? So this is the definition of conditional probability for given set B with probability different from 0. Then multiply probability of B both sides of this equation. Then we have probability of A intersect with B equals to probability of A given B times with probability of B. It means that if you can have the, they give you the probability of B and you know probability of A given B, you can compare probability of A intersect with B. And this is an example. Okay. Can we try to use the multiplicative rules to find the probability of failed alarm? So if I put A1 is an event that the aircraft is not present, and B is the event that the radar detects an aircraft. So this is the So this is what happened? Okay. So this is my definition for the event. Can I compute probability of A1 intersect with B, which means that a fail indication of an aircraft presents, which means the aircraft is not present, but the radar detects an aircraft. What can I have from the problems? From the problems, if you have a look at the second sentence, if it is not present, which is the aircraft not present, then the radar register an aircraft present with a probability 0.1. So which means that probability of B given A1 is 0.1, right? And we have probability of A1 is the probability of the complement of an aircraft is present is 0.05, which is 1 minus 0.05 is 0.95. So using the multiplication rules, so you have probability of A1 intersect with B is probability of B given A1 times with probability of A1. And you have everything from the question, you just put them together and then you have the result. All right, so this is an example to use the multiplication rule to find probability of the intersection of two sets, given that you know the conditional probability and probability of A1. Okay, can we try to compute the second question, probability of misdetection? Can you try to use the same method to find probability of misdetection? Of misdetection, which means that an aircraft is present, but data doesn't detect the aircraft, right? So which is, I put A2 is the aircraft is present and F is data doesn't detect aircraft, then I need to compute the probability of A2 intersect with F. So from this definition denote for A2 and F, so I can say that probability of F given A2 is, which means that probability of data doesn't detect an aircraft given that the aircraft is present, is here, from the first sentence. The first sentence is the probability of radar detect the aircraft given that the aircraft is present is 0.99. So then the probability of radar doesn't detect aircraft given that aircraft is present is complement of that one, 1 minus 1, 0.99. T9, which is 0.01. And we have probability of A2 aircraft is present is 0.09. So, right, 0.05. So then just using the multiplication rules to find the probability of the intersection, times these two numbers together. So you have the result. Okay, so we have the way to compute probability of the intersection of two sets by using the information of conditional probability. So the question is that can we compute the intersection probability of intersection of three sets from the information of conditional probability? So I want to compute probability of A1 intersect A2 intersect A3. Okay, if I group the first, what is the way to write? A1, okay. So if I group these two together, so now I have green set intersected with A3. So using the definition of 2, I have this one is probability of multiplication rules. It's probability of probability of the green set intersect with A3 equals to probability of the green set. Let me see which way for the corresponding with the lectures. A3, okay. Okay, so A1. A1. So it should be like this. Okay. So this one is probability of A1 given A2 intersect with A3 times with probability of A2 intersect with A3, right? This from the definition of conditional probability or from the multiplication rules. So you can compute the probability of the intersection of three sets. Okay, for the general case, when we have the intersection of n set, in the condition that if we have probability of the intersection of the first n plus minus 1 set is not empty, then you have the following formula, which means that you can compute the probability of the intersection of AK for k from 1 to n will equals to the product of probability of A times with probability of A2 given A1, then times probability of A3 given A1 intersect A2, and up to AN given the intersect of AK from 1 to n minus 1. So to prove this equality, you can just take the right hand side and then expand what is the definition of the yellow term. The yellow term is probability of A2 given A1, right? So from the definition, it is probability of A2 intersect with A1 divided by probability of A1. And then the blue term here from the definition of given conditional probability, you have the blue term equals to probability of A1 intersect A1, A2, A3 divided by probability of A1 intersect A2, right? And then so on for the last term, the green term here, using the definition of conditional probability, you see that is equal to probability of intersect of AK for k from 1 to n divided by the probability of intersection of AK just k from 1 to n minus 1. So now look at this one. You can see that you can cancel out A1 here, property A1 here, right? And probability of A1 intersect A2 can cancel out with probability of A1 intersect A2 here, so on. Then, which means that this one can cancel out with the term, the previous term, somewhere here. Then the last one is the red term, which is the probability of the intersect of AK for k from 1 to n, which is equal to the left-hand side. So now you can prove this inequality just using the definition of conditional probability and expand the right-hand side, then you can obtain the left-hand side. Or you can use the method of induction. Yeah, it depends. Okay, do you have any questions? Okay, so we have so this is an example. So you have a set, an omega sample set omega like this, and then you have A1, A2, A3. You have B as the rectangular in the between here. So this is B. This is B. This is so this is B, right? This is A1, this is A2, and this is A3. Now the question is that if you know the probability of A1, A2, A3, and you know the given. If you know probability of A1, A2, A3, and you know conditional probability of A1 given B, you know probability of A2 given B. Of course, you don't need to know the last one, right? Then can we compute probability of B? Actually, you don't need the last one because A1, A2, A3. What is the name for this property? A1, A2, A3 disjoint and union is the whole sample space, omega. Did you learn it before? Partition. Did you learn partition? Okay, so, okay, so A1, A2, A3 are partition, right? It's a partition. So you don't need this one because probability of A3 will equals to 1 minus of the sum of these two probability. And the last one here also equals to the 1 minus the sum of these two probability. Actually, you don't need this. Okay, so given probability of A1, probability of A2, probability of A1 given B, probability of A2 given B, can we compute probability of B? Yes.
Wouldn't it be probability of B given A1 and probability of G given A2 that we're given?
B, yes.
So we can solve for some of the intersection.
So what is the probability of B? Probability of, okay, probability of is that probability of B equals to probability of this area plus with the probability of the green area and then plus with the probability of the blue area, right? Because they are all disjoint and partition. The red, green, blue area is a partition of B. Then how can we compute probability of the red rectangular? This one is the probability of the, this one is probability of A intersect with A1, B intersect with A1, right? And the blue-green one is probability of B intersect with A2. And the blue area is the probability of B intersect with A3. So now just using the multiplicative rules, then you can compute probability of A intersect with B intersect with A1 is, do I have it? Is here? I don't have it here. So I just, so now you have probability of B equals to probability of B intersect with A1 plus probability of B intersect with A2 plus probability of B intersect with A3. Right? This one, the first term from the multiplication rules, you have this one is probability of B given A1 times with probability of A1, right? This one is probability, the second term is B given A2 times with probability of A2. And the last term is probability of B given A3 times with probability of A3. Okay, so this equality have a name. It's called the total probability theorem. So for the general case, if you have n set A1 up to AN, and this all is a partition of omega, which means that the union of all these sets is omega, and they are disjoint. And they're disjoint. Then you have okay. Then you have a similar equality like this one for the simple case of just three sets from A1, A2, A3 from a partition of omega. So the way is that probability of B equals to probability of B given A1 times with probability of A1, and then you plus with probability of B given A2 and times with probability A2 up to the last one is probability of B given AN and times with probability of AN. To prove this equality in general, you can take the right hand side. So put the right hand side is the whole of this one. Then you just using the definition of conditional probability, you can see here the green term. The green term is probability of B intersect A1 divided by probability of A1. So now here you can cancel out this one. Cancel out A1 here, probability A1 here. And then the blue term, the conditional probability blue term equals to probability of B intersect with A2 divided by probability of A2. And then I can cancel out probability of A2 with the probability of A2 here. So similarly, the purple term is probability of B intersect with A1 divided by probability of AN, intersect AN and then divided by probability of AN. So then I can cancel out probability of AN here and probability of AN here. So now you see that the right hand side in the end equal to the sum of this probability. And because A1, A2 up to AN are disjoint, which means that B intersect with AN, B intersect with A2 up to B intersect with AN also disjoint, right? So then we have the last one is that come from this. So since AK, for K from 1 to N are disjoint, then we have the sequence of the set intersection B intersect with AK for K from 1 to N also disjoint. Therefore, we have this sum of the probability equals to probability of the union. And union of all B intersect with AK equals to B intersect with the union. And because union of AKs is omega, because AK is the partition. So that's why I have the blue union is omega, and B intersect with omega is B. So this one is probability of B. So at the end I can prove that the right hand side equal to probability of B, which means that you have this equality. So the proof is quite simple when you just apply the definition of conditional probability for each term in the right hand side, and then can do some calculation using the probability of the disjoint set, union of disjoint set equal to the sum of probability, and then using the property of the partition, then you can have the end step, the last step. Do you have any questions? Okay, so we go to the last rule we learned today is called Bayes rule. The Bayes rule actually is come from the combination of multiplication rules and the total probability theorem. So it is, first I have a question. What is the relation between probability of A given B and probability of B given A? How do we compare probability of A given B and probability of B given A? In order to write probability of A given B, what condition do I need? In order to write this one, what assumption or what condition do I need? So I need assumption that probability of B different from 0. And to write this one, I need assumption that probability of A different from 0. Yeah. So now what is the relation between probability of A given B and probability of B given A? Just write it from the definition. Is anyone have the answer? Yeah. Yeah, just write from the definition of conditional probability, this one equal to probability of A intersect with B divided by probability of B, or using the multiplication rules, you also can have the final answer. This is intersection B divided by probability of A, right? So now, which means that probability of B given A times with probability of A equals to the probability of the intersection, right? And this one, you have probability of A given B times with probability of B, so equals to the probability of the intersection. So these two, they're the same number. So that's why you have probability of A given B times with probability of B equals probability of B given A times probability of A. So this one equal to this one. Okay, then for the Bayes rule, so if you have A1 up to AN is a partition of omega, then you can compute probability of any AK given B. So this one is come from the definition of conditional probability, right? Probability of AK given B equals to probability of B intersect with AK divided by probability of B. This is the definition of conditional probability. And then the blue, the yellow line here, the yellow term here equals to probability of AK times with probability of B given AK, which is also another way of the conditional probability, right? So you have this, and then using the total probability theorem, you can write probability of B by the sum of conditional probability, B given A1, B given A2, up to B given AN, and corresponding term multiply with probability of A1 up to probability of AN. So which means that the green term here equals to the green sum. And the reason is that because we have AI is a partition of omega, so we can apply the total probability theorem. So that is called Bayes rule. So here an example using the context of the previous example, and then now we want to compute the probability that an aircraft is present given that a radar registers the presence of an aircraft. So using the Bayes rule, then you can compute the probability of A2 given B. So A2 is this one, and B is this event. Do you have any